All right, I think we're good to go. All right, good afternoon, everyone. My name is Maaz. Thank you so much for being here. Today, I'll be presenting my capstone report, and the title of the topic is a research on construction progress monitoring process using an automated robot. Before I begin, I just want to mention how fun this entire 6 to 7 month journey has been for me, and that this whole process of going through this research has been like more exciting than I actually expected it to be, and I'd like to thank Professor Kim and all the committee members for helping me throughout the process. So thank you for that. So yeah, let's officially begin with what we'll be covering in this presentation. And again, if you have any questions, please feel free to interrupt me, stop me. I want it to be two ways. Yeah, whenever you have a question or something's not clear, please feel free to stop me and ask a question. Yeah, so in today's presentation, we'll be starting off with the general introduction. What was the background? What was the rationale for choosing this research, specifically this topic? What were the things that went behind the scenes that made us come eventually to this research topic? Then we'll be moving on to the research aim, objectives, the scope, the design. From there, I'll be moving on to the literature review, some of the important points that were pertinent to mention in this presentation. After that, I'll be covering the research methodology, and then we'll get started as to how did we go about the process of collecting data. This presentation talks about a robot. How did we go about procuring that robot? What was the selection process? What was the modification process? How do we program it? And then eventually, I'll be showing you guys a video of the trial that was conducted. Once that's done, all that initial data gathering process is done, I'll be moving on to how we analyze the data and eventually came towards the final recommendations for future research and the conclusions for this research. So just starting off with basic background rationale, what is the importance of progress monitoring in construction? Well, if you'll ask any construction guy, we understand that it's important in most construction projects in the current architecture, engineering, and construction industry. As a project moves on, it's essential to ensure that the project is on track and on schedule. From my personal experience, from the experience through this research, and from listening to the respondents' feedback, I've realized that this is more of this progress monitoring has more importance towards the commercial side of construction rather than the residential. Just to throw that out there. So now that we know how or why progress monitoring is important, what was the conventional or the traditional progress monitoring process? So initially, we did progress monitoring through visual inspections. A person would go out on the site and see how things are going. Were the daily tasks that we had to do, are they complete? If not, what can we do to improve them? Basically, a superintendent or a site personnel would go on site and look at how things are happening. And that's how conventionally it was done. Now, how is it done contemporarily? How is it done in the current world? Well, with the advent of digital technologies like photogrammetry, laser scanning, we have moved on from only visual inspections and into the world of digital progress monitoring and tracking. So now, not only do we have visual inspections, but to add on to that, we also have, we use digital photos, we use 360 photos, we use drones, different technologies to monitor progress. So this is besides visual inspections, which are still being carried out alongside digital progress monitoring. So to understand basically why progress monitoring, why is this something that we wanted to automate? We need to understand that this progress monitoring task for especially big projects is something that's an ongoing, often daily task that's carried out throughout the life cycle of a project, which can be several years at a time for certain projects. And that can become arduous and monotonous for the person carrying it out every single day, repeating the same process over and over again. So where does this concept of automation even come from? We see that this concept comes from the manufacturing industry. When a process, as I said, when a process was being carried out repeatedly over a long span of time, people figured out, why don't we automate this process and let machines do this process rather than humans who are actually prone to making mistakes. So that's kind of where the word automation or the concept of automation comes from. Now, these machines that people said, let's try to use these machines to do these tasks for us. These machines that are automated, they're currently called robots. And now this word robot, it actually comes from a play it comes from a play back in 1920. And from my personal research and through lit review, it was kind of interesting to see how a lot of the research papers that you'd see about automation and robotics, they'd use the term robot, but they would not define it. And you can go all the way back to 1920 to when people started using it. Everyone knows what a robot generally means, but in the academic literary sense, what does it actually mean? What's its definition? You could not find a literary definition up until this recent paper by Maaz et al., who defined the robot as any actuated system capable of performing tasks or actions for people with a certain degree of autonomy. And this is kind of the definition that we'll be using for the general purpose of this presentation and this report. So what is a robot then? A robot is simply an automated device or a machine that performs complicated and often repetitive tasks. And as I mentioned previously, they're better at doing these tasks as compared to general humans. So as I mentioned earlier, once we had this concept of automation, we saw that this progress monitoring process is something that can be automated because it's something that goes on for several years, often daily, weekly, and is something that's repetitive. This is a process that can be automated in construction. So from this point onwards, we decided to review the current literature about progress monitoring and automation. How has progress monitoring been automated in the past, and where does the current literature stand in this regards? Once we started reviewing the current literature, that's when we saw a gap. And this gap was, academia says a lot of potential, that there's a lot of potential in the concept, but there's no actual validation from people in the field, the construction industry, regarding the concept. So when we saw that, that's kind of what we focused our research on. And that's kind of the basic background and rationale for coming up to or arriving at this topic at the end of the day. So moving on to the background and rationale, once we conducted that literature review and we saw that gap, that's when we moved on to the research aim. That's kind of when we figured out, okay, we can actually add on to the current body of knowledge in the current literature that's present. The way we did that was our aim came out to be to investigate whether there's a need and a penchant towards automating digital process of construction progress monitoring in the current US construction industry. So basically to understand whether or not there's a need, whether the current practical world out there, whether or not they even want to use this technology and automate it for progress monitoring. And then we had 6 objectives that we formulated from that. And the first one comes from the aim, industry validation of proof of concept, whether the current industry would like to delegate progress monitoring of projects to automated robots due to repetitiveness or monotony. From then on, how do we do that? How do we do this proof of concept or this industry validation? The next steps were kind of the methodology of how we ended up doing it. So the second objective was to develop a prototype robot with an attached 360 camera. The third was to automate or semi-automate the progress monitoring process via programming the robot. The fourth was to test the robots working in a mock environment. We went to the Robbins and Morton construction field lab that's recently constructed. That was our construction mock environment. and then to solicit feedback from construction personnel on the applicability of this concept in the industry and for further improvement of the prototype. So that's kind of where we're starting to gather the research data from, um, from the trials that we conducted in that mock environment. And then lastly, we did a SWOT analysis by using, obviously, industry feedback, using the RoboMaster S1 and the camera for construction progress monitoring. So moving on to the scope and the design of the research. The scope of this research was limited to the willing participants associated with the U.S. construction industry. Everyone had a choice whether or not they wanted to participate in the survey, and that's kind of how we limited it to the U.S. construction industry. The duration was 6 months from February to July right now. And talking about the design, COVID-19 has been a big, I guess, has been something that has really changed a lot of our world as we know it, about a lot of the things that we currently do. So pre-COVID-19, we had an initial design, and that initial design was that we would take this robot that we have modified and automated, we would take it to actual construction sites, and we would conduct in-person trials on actual running construction sites. And once that's done, we would collect data through interviews from say the superintendent, from field personnel, to get qualitative data. So initially it was just qualitative research for industry validation. But then COVID happened in February, March-ish time. And then we moved on to a mixed methods research. And the on-site in-person trials went to surveys and making a video that shows the robot working, that we'll be seeing later on in this presentation, and then getting feedback from that. So that feedback got us qualitative data, but the number of respondents in the Qualtrics survey for and against certain point, that gave us our quantitative data. So that's how this research became mixed methods in design. Now, moving on to some of the important literature review points. There were 4 basic questions that we focused on when we were going through this literature review process. The first one was, what are the different construction processes that have been automated using robotics in the past? So trying to understand like what different processes have been automated already. The second one was, what are the current obstacles, issues towards the adoption of robotics for progress monitoring in the construction industry? What are the issues, what are the obstacles that are being faced for the adoption of automation or robotics or even similar technologies in the construction industry? What does contemporary research have to say about the mitigation of these issues, if anything at all? And then lastly, how can this research, our research, help bridge those gaps? So the first 3 points were basically what we got out of the literature review. The last point was trying to put all that together to eventually get to this research and to find a gap that we could work on. So one of the first most important things, what are the different construction processes that have been automated using robotics? So this was from a paper by G.M. Delgado, and he talks about 4 separate categories that are being the technology that is being used and that is being automated in the construction industry. So he talks about offsite automated prefab systems, and in that he talks about large-scale prefabrication, additive manufacturing. So a lot of the manufacturing stuff in construction for prefabricated work, that's being automated. And then the second thing he talks about is on-site automated and robotic systems. And these robotic systems are basically single-task construction robots. We've heard about bricklaying robots and steel truss assembly, steel welding robots. These are more like single-task construction robots that carry out a single task, and they keep on repeating it and doing it over and over again. And then robotic on-site factories, swarms and robots for building component assembly. So this was basically the second category. The third category is kind of what we're interested in. This is the third that he talked about. And these were terrestrial, aerial, or nautical vehicles that can be piloted remotely or which are autonomous, access to extreme and dangerous environments, surveying, inspection, and monitoring, basically our research, and automated drilling, excavation, and earth moving. Now we have like excavation and earth moving trucks that are being automated currently in the industry as well. The final thing that he talked about, exoskeletons, he mentioned that exoskeletons, they're not currently being used in the construction industry, but sooner or later, he said that this is something that would add on to human physiology and help us improve tasks and improve capabilities of, say, workers and people who are actually building the building itself, and improve their capabilities and productivity altogether. So this is kind of an overview of like what are different construction processes that are being automated or have been automated using robotics in the past. So moving on to what are the current obstacles, issues towards the adoption of robotics for progress monitoring. The number one issue or the obstacle that we face is the adoption of technology. And to understand this, if we compare it to the manufacturing or some other industry, we see a big difference. And to understand why, as to how or why this is an obstacle, why is adoption an obstacle, there were three things that came out from this research by Ali and Yitman in 2019. The number one thing was cost. The second thing was skilled staff. And lastly, it was about lack of information about the impact of automated progress monitoring on project performance. And this third point is basically what his research mostly worked on. And to understand what his research actually came up with, or how did he talk about mitigation of these three issues that we talked about, he mainly dealt with the third issue, which is a lack of information. And the way he did that was, his main findings were, he dealt with three key performance indicators: cost, time, and quality of construction. And the conclusion of his research was that cost and time were improved using automated progress monitoring through digital capture of images. Now, how did he do that? He did that through two things: structural equation modeling and benefit analysis using literature, current, present articles, conference papers, and journal papers, and actual construction projects. Now, so what he basically did was he analyzed different construction projects. He analyzed different papers that are talking about automation in construction progress monitoring, and he did an analysis and figured out that two of the three key performance indicators, cost and time, are being improved if this technology is introduced. So what he did through his paper was he tried to cater to this third point, the lack of information about the impact of automated progress monitoring, and try to tell people, try to tell the industry, or the academic industry at least, that this is something that can actually help the construction industry if it is implemented or if it is applied. Our research, on the other hand, not only deals with the third point, which by his paper was just academic in nature. Our research deals with the cost, skilled staff, and also the third point, but our research deals with it in a more of a practical standpoint, in more of an industrial standpoint, trying to bridge the gap between what academia knows about automation and progress monitoring, that it is something that should be done, and what the industry knows and whether or not they want to do it or not. So moving on from that, another thing that was a main point in my literature review was technology development. What is the technology that is currently being developed? I saw that there's a lot of focus on unmanned ground vehicles rather than unmanned air vehicles, and the main reasons that were mentioned for that was the fact that UAVs, it's hard to automate them, and they have a lot of issues when you're modifying them, especially in terms of added weight and flight times. So currently there are two researchers, one by Peel H in 20, that's he has published a paper in 2018, and Asadi et al. In 2018 as well. And they're currently working on, Peel is working on monitoring of a bridge project using a robot, and Asadi is actually working on developing a robot for general construction monitoring and purposes. So they're working on the technology itself, basically research and development. And their goals are basically to develop a robot that can autonomously navigate a construction site, number one, and two, have enough processing power to seamlessly process visual data in real time to produce results for construction personnel. And this is something that the technology of it is currently, it's in progress and it's going on. So from this literature review that we conducted, we noticed a gap. And this gap was that there's theoretical proof present in literature. We see that there's a lot of working on the technology that's being conducted. There's a lot of R&D that's being conducted for the technology of robotics. But there's little to no practical validity from construction industry. And that is something that we saw as a gap. So would the utility of this concept of progress monitoring at the end of the day yield added value for construction personnel? This is something that we decided that we should see and hear from actual industry personnel and try to get their feedback. Companies like Doxon and Boston Dynamics are already working on practical validity, but from a business standpoint, because they have a product that's ready and they want to market and sell it, they're not per se as neutral as an academic person asking industry feedback who has nothing to do with the sales or marketing of a product would get to. So thus this research's aim, which was again to investigate whether there's a need and a penchant towards automating digital progress, construction progress monitoring in the current US industry. So moving on from that initial literature review, background, rationale, let's talk about what we actually did for this research. So first off, and this is just a general flow chart, we conducted literature review, we purchased and assembled a robot and equipment, modified the robot for camera attachment, programmed the robot for autonomous operation. We set up a mock construction environment, we run trials in that mock environment and recorded videos. We processed that video and sent it to interested general contractors, builders with a survey for feedback. Lastly, we analyzed that feedback, and eventually we're at this point where I'm presenting this capstone. So let's talk about research data gathering for a second. So what's the process? How did we gather research data? This was kind of covered in the methodology as well, but because there's something that we worked on quite a bit, so I want to go a little in depth in this. So this is the overall process that we conducted for the research data gathering. Let's talk about the first step, choosing a commercial robot. The robot that we ended up choosing was the DJI RoboMaster S1. You can see it in the picture right here. And the factors that we considered that ended up helping not only choose this robot, but also helped us choose an unmanned ground vehicle, a UGV, rather than a UAV, are these five. The first one was programmability. Can the robot easily be programmed? The second thing was operational time. Third thing was modifiability, ease of use, and cost. And these factors help decide between unmanned air or ground vehicles and eventually this robot. Let me talk about UAVs for a second. A lot of the UAVs that are programmable at this point in time, especially educational UAVs, they're not only small in size in nature, but their flight times are also limited to about 7 minutes to 13 minutes. A lot of the non-programmable UAVs are the ones that are actually more advanced. They're used for video capturing or drones that we generally use in construction. They're actually of good quality. They're actually pretty sturdy, and their flight times are, say, 20, 30 minutes. That is kind of what we needed, but they were not programmable. Programmability was not a thing that was included in those robots. Those robots were generally made for surveillance purposes. So a lot of the programmable UAVs were really small. Their operational time was really minimal. Modifiability was one of the biggest problems that we had with UAVs. Because they're flying in the air, they're usually really nimble. They're made not as capable of carrying huge loads. And that was something, because we had to modify that robot and attach 360 camera on top of it, that is kind of one of the reasons that we said that, like, let's not go with UAVs. UGVs were something that we could actually modify much more easily. So these first three things were the major factors that ended up skewing our decision towards unmanned ground vehicles. And then,
question, was size a consideration on the robot? I noticed it's a pretty small size. Did you have other options that were of different form factors, and you decided on this one?
Yeah, so when we were looking at UGVs, eventually we ended up looking at two of them. One was this robot, the other one was called Husky. It was a little bigger than this robot, but its programmability was an issue. And if you're talking about size in terms of it can like pass bigger terrains, this was kind of the best robot that we could find at that point. That not only was easily programmable, had a good operational time, was modifiable, and it was easy to use, and it was cost effective. Size was not really a consideration at this point of the research. So yeah, so again, the reason why we considered this was it's easily programmable. It uses Scratch programming language, and I'll talk more about that as we move on in the presentation. Its operational time, as you can see from the specs right here, it's easily programmable using Scratch. Scratch is a programming language that's taught in primary schools. Its average continuous operation time is of more than 90 minutes. Its weight was 7.6 pounds. Its height was 10.6 inches from off the ground. Yes, pretty small, just like Steve said. But an important point that a lot of the construction personnel have issues with is the cost. And this costs only $550 as of right now, July 2020. So these
question. So the programmability seems to be like one of the big considerations as well.
Definitely.
Do you foresee like construction companies doing the programming themselves, or are you saying in terms of for developers, it's going to be easier to use a easily programmable robot?
Are you talking about are you asking about this robot specifically?
Yeah, or just in general for the study. Do you foresee the construction people programming their own robots?
Okay, yeah. So this was one of the biggest concerns because programming is something that's usually not inculcated in general construction. If you ask someone to program something, they'll be like, no, like I'm not gonna do it. Generally, the other robots that were bigger in size that were programmable had Arduino chipboards and used Python programming language and really complex programming to actually even make them do really simple tasks. This Scratch programming language, and I'll talk about this more as well, a person with no background in programming, and by no I mean zero background in programming, can learn to automate what I automated basically in less than a day, what I automated for this research. And the reason is you don't need to know any syntaxes, you don't need to know any detailed programming. This is made really interactive, actually for kids as well. And all you have to do is, and I'll show you the program as well, all you have to do is take the code, put it here, and the code says move at 0 degree for 10 meters. And you can change the 0 degree to like change the direction, you can change the number of meters, and all you have to do is like slide it using your finger in the app. So that's why like it's really easy and pretty intuitive and super easy to learn. Talking about the selection of the camera. So the camera that we used is this camera right here. It's Insta360 1X. An important question should be why 360 cameras? Why not just normal 2D cameras that often come with robots like this? And the basic reason for this was that when I was like going through my literature review, I saw how 360 cameras are being used more and more in the construction industry as we go on. And the basic reason, the primary reason for this is the utility of a 360 picture for inspection as compared to a 2D picture. In a 360 picture, you can have thousands of frames of different angles from that specific point. It's kind of like standing at a point and looking all around you as compared to a 2D picture, which is just focused on a specific frame. That's kind of why we were focused on, we want a robot that either already has a 360 camera. If not, we're going to modify it. From our research, we saw that almost no drones at this point in time that are programmable and no UGVs that are programmable had 360 cameras. So this was something that we had to do ourselves. And the factors that we considered for this selection was obviously, as I said, a 360-degree camera. It should be compact, the smallest design possible, because we're putting it on the robot, obviously, good photo video quality, and cost. Again, that's important. So the specs for this camera right here, it's 80 megapixels. It monitors live video from your mobile device while the robot's, say, traveling, or if you're like taking us somewhere. It has a 60+ minute battery life, 4K video, gyro stabilization, which is really important. Like, this is something that a non-technical person who doesn't really know much about cameras can easily be like, okay, this is just jargon. But this was important for us because when we actually took this camera on construction sites and we had the robot traveling and even like going through a couple, some gravels or some rocks, the gyro stabilization in this camera almost stabilized and made the entire video smooth. Like, we did not have that distortion that you normally have if you're carrying something around or something moving up and down. So that was really important. And then its weight is just 115 grams without any other attachments. And again, minimal cost, $400. So that's, if you can see, a $550 robot and a $400 camera. That's almost like $1,000 in like basic installment as compared to like what we currently have in the industry that are like almost $80,000. Let's move on to the modification process. How did we modify it? And this was kind of where, when I said this research was really fun, this is kind of where I really like started to explore and be creative throughout the entire process. So these three masks that you see on your left, these are kind of the first three versions of the mask that we created to place on the robot. We realized that if you have to attach the camera on the robot, we need to have a mask that attaches onto it. So we got this basic attachments, and I had to like be creative and make these two different masks. As you can see, this right here is a simple selfie stick. This is a simple rod. This selfie stick can get extended. At the bottom, we have these three different shoes. These shoes can attach into this shoe holder. It just clicks right into it, and you can also take it out of it. And right here is we have a 3M double-sided tape that we decided to place on top of it and attach it over there. This big thing right here is actually the dust impact or waterproof casing that we had for this camera, so that the camera doesn't get damaged in case it's raining or in case it falls or something. Now, this is kind of where, when we talk about research, like whenever you're doing something new, you're always bound to fail. So this is kind of what happened. These are the first two trials that we conducted. Ideally, we wanted to have a mask that was super tall, 6 feet tall, almost a human height, that can capture videos from a normal human height. But because this robot was not as sturdy, because it had limitations, this mask right here cannot stand for more than, say, 10 seconds. As soon as I took this picture, it fell right away, kind of like how you see on the mask at the left. So both of these masks, because of their weight and because of the robot's head not being able to support that weight, it could not keep it straight. And that's kind of why these two failed. Eventually, we came on to this little guy. This is the final modification version of the robot. And this is kind of something that this robot's head and its gimbals and its motors inside its head could actually take and move with. The factors that were kept in mind were the mobility of the robot with the mask. It should be able to move. Robot's unobstructed gimbal head rotation. We wanted it to be able to rotate its head without any issue. Later on, we discovered that even if it doesn't rotate its head, even if its head is up or down or left or right, it doesn't matter for our pictures at the end of the day, because they're 360 photographs and they're just going to take everything around it. And then unobstructed view of the cameras, the robot's view cam, which you can see this thing that looks like a one eye on its front, and then the 360 camera. We did not want to obstruct that. Now, while I was going through this limitation process, there were, modification process and the trial process, these were some of the limitations that we found that the robot had. And this is something that's important for anyone who's carrying this out for future research purposes. This is something you want to keep this in mind. You want to keep in mind. So the 360 camera weight of the small mask that we actually ended up using, it put a lot of strain on the robot's head, which would make it eventually sometimes go to safe mode to prevent overheating of the robot's motors. And as soon as the robot goes in safe mode, it stops holding its head at one place, and you're unable to control the head anymore, and it just freely rotates wherever it wants. The second thing was that the head, as soon as you move the head plus minus 15 degrees in the up or down direction, it goes all the way and gets stuck either all the way up or all the way down. So you have to make sure that manually, while you're controlling it through your laptop or your phone, you don't move it up or down too much. Otherwise, you just have to come in and fix it up yourself. 0 to full acceleration or vice versa. If you accelerate it or decelerate it too fast, the same problem happens. But again, as I said, even if the robot's head is stuck somewhere, the 360 pictures are unaffected because they take everything around it. And then one of the things that we noticed was the battery lasts for more than somewhere around 60 minutes of constant use on a single charge. Let's move on to some of the fun parts, programming the robot. So as I mentioned previously, and also like answering Steve's question, this robot had its own app, and in that app you had these guides that literally took your hand and took you through basic processes to automate this at the end of the day. So it had beginner guides, it had advanced guides, but to like actually do what we did for this project, we didn't have to go all the way. The beginner guide for basic movement was enough that I was able to master in about 2 hours, honestly. This is the program that I created after going through that trial. This was done in Scratch language. As I said, I watched the tutorials, learning less than 4 hours. And let me explain how, just a basic overview of like what's done. So as soon as you start, you have this basic start box, and then on the left side, you have all these different options that you can choose from. So the first thing that you're supposed to do is you're supposed to set the speed that you want it to translate. So you'll take this tab and you'll pull it out and you'll place it in the start tab. That's all you have to do. And then you'll tap on 1 meter per second and change it. Then once you've set the speed, you want to move it on a certain direction for a certain amount of time. So you'll take this tab, you'll slide it, and it'll plug itself automatically in place. And then you change that to 0 degree. That means it's moving straight for 7 seconds. After that, set chassis to rotate. It will rotate. You can choose left, right, back, whatever you want here, different options. And then at 90 degree, you want it to rotate left at 180 degree, it'll turn all the way. You can choose different options here. And once that's done, this is kind of how repeating these 2 to 3 things. Another one that I used was this. In this translation or movement, I did it for 0 degrees for 7 seconds. Another thing that you could use was, instead of time and speed, you could set it for direction and distance. If you want to go for 2 meters, 3 meters, 10 meters in a certain direction.
One quick question on that. The navigation seems very prescriptive, that you're programming angles and distances. And on a really large building, do you foresee having issues navigating around a large building with remembering all these distances and angles, and not having necessarily like a GPS or something to navigate by?
So yeah, and that's actually a good question. For the purposes of this research, because we only had to show people that robots and a robot can be easily automated, and this is how we monitor progress, this was enough. But this robot has capabilities that you can actually program it for line tracking. So you can actually, not only line tracking, it also has human tracking. So basically what you can do is, if you're talking about lines, someone can just attach a tape on a construction site. You can choose the color, red, green, blue, it has different colors in it, and you can make it go throughout the path that you want the robot to translate at, wherever you want it to go. And basically that robot would follow that line all along. So that's kind of application. Yeah, that's kind of one of the things that would help in that regard. Also, it's also got not really obstacle detection, but if it hits into something, it will recognize that. So you can program it in such a way that as soon as it hits into something in whatever direction, it will do a certain task. It can say something. You can record a voice and have it to play. It can go back. It can stop. It can do whatever you want. So these are some of the things that you can introduce in it. yeah, this is the basic program. This is the basic how the program looked. I used a combination of these 1, 2, 3, and 4 um, tabs to basically play around with the entire thing and actually make the entire program. The way this program, once I learned how to program it, I went on the we went on the actual trial site, the Robert De Morton Fee Lab, and actually decided, okay, this is what the path is going to be. This is what we're going to have the robot translated and develop this uh, program according to that. It took honestly about 10 to 15 minutes to do it on the site. So let's move on to what that trial actually looked like from the program that we developed. And what was the video that we actually ended up giving to all these respondents in the survey. So let's go through that. And let me know if you can't hear it or if the voice is not clear due to some reason. Hi, thank you so much for your time. I'm Maaz, along with Professor Jeff Dent. We're trying to research on what general contractors like yourselves have to say about robots monitoring digital progress on construction sites. For this purpose, we've developed a small demo for you to see, and then to give your opinion about whether or not you think that this concept is something that you'd be happy to see on construction sites in the future. It is pertinent to mention that we're more focused on the automation process itself rather than the robot. To help us understand if automating this process provides value for you, your company, and construction as a whole. Thanks so much. This is basically the trial that we decided we're going to run on. All right, so that was a brief overview. That was actually the video that we showed to the industry personnel in the questionnaire survey that we prepared. And we basically got a before and after opinion from them on the research question that we asked. I do want to mention that the 360 pictures that you see, that you can see it like that when you spread it out, but usually when you'll be monitoring actual progress, you'll be going on to actual frame. So you can see the entire, everything around you, just like a normal picture, and you can pan around and see different things. So that being said, let's talk about the questionnaire survey preparation. Excuse me for that. All right. So the main aspect that we tried to focus on while preparing the questions for the survey were, number one, brief information about the survey taker. What is his role in the construction industry? What does that person do? Brief information about the company they work at. What is the volume of work that the company does? Whether or not they have a BIM department at the company. And then we try to understand where their current knowledge stands regarding the process of automated progress monitoring. And this was important because this kind of helped us understand the perspective that these people were coming from individually. And then we also asked them about what their current thoughts were about the process, about this process in terms of safety and pragmatic utility. And then we made them watch the video that you guys just watched. And then after that, what their thoughts are after watching the video that depicted the process being carried out. And then once they shared their thoughts with us, how did it change? How did their perspective shift? Did it shift? Did it not shift? We basically asked them to tell us about that. And then lastly, we made them sort of do a SWOT analysis in which we gave them different attributes and asked them, hey, do you think safety is a strength, weakness, opportunity, or a threat for the process? We also talked about reliability and different things that I'll mention as we move on. And then lastly, we asked them what they would have liked to see differently in this process or in this research, or just their personal insights about the entire experience. That's kind of what the whole questionnaire had in and of itself. So let's move on to the data analysis and results. So now that we know how we gather data, what was the whole process that we went through to gather the data, let's talk about once that data came down to us from the research questionnaire survey, how did we analyze it? So these are some of the different steps that we did. We conducted personnel analysis, construction firm analysis, tried to understand where their knowledge stands before watching the video about automation and progress monitoring, and then ask them about their perception before and after. Did it shift? Did it not shift? Safety analysis, and finally a SWOT analysis. So from the personnel analysis, we had 40 complete responses in the 2 weeks duration of the live survey out of 53 total responses that we received. The 13 responses that we did not consider for this analysis were because they were less than 60% complete. And looking at this chart right here, these are some of the roles of the survey responders. So we had, as you can see, we have the most people that we have are project managers and company executives, and the least we have are superintendents and laborers. And this is interesting because we sent this out to companies. Generally, people in their offices, I don't really know why this happened, as to why less superintendents decided to respond to this, but we had more project managers who decided to respond in companies. I do think if we would have gone to actual construction site in a pre-COVID area, we would have had more responses from superintendents who we'd have been interacting with if that happened.
Of those who didn't complete the 60% of the survey, do you know general job titles of that group? It'd be kind of interesting.
The general job titles of that group?
I'm just curious if those are the superintendents that only got 60% or less through.
Well, that's actually a good point. I knew like this general trend followed. I did not actually go and look whether or not they were all 13 superintendents that I ended up canceling out. I hope not. I think this was the general perception, but yeah. So the 4 people that did respond as others, they said that one of them was scheduling manager, a safety coordinator, a construction technology manager, and a director of pre-con. And then the demographic locations where these people responded from, we had actually targeted companies in the Southeast more, and we had also like sent the survey out to AGC, Alabama, and Georgia. So we have 32 responses from Alabama, 4 from Georgia, 1 from Florida, 1 Washington, and 1 California. And these were some of the outliers in the demographic. Moving on to the construction firm analysis, we asked them, BIM and does your company have BIM or VDC departments? 25 of those 40 people responded that they did not have VDC departments at their companies. 15 companies responded with a yes. And to understand the annual sales of work for those companies, and the reason we asked them the annual sales of work, we also tried to understand whether there was a correlation between having a VDC and a BIM department with their annual sales or volume of work. And so basically we had 52% of our respondents, that's more than 20 respondents, actually 21 respondents, that said that their company lies in the $1 million to $100 million range. That's kind of like the medium-sized firms. We had 17% to 20% ranging from 100 million to 1 billion. Companies that were greater than 1 million, the really huge firms were 17.5% of 40 respondents. And then we had 5% each of the companies from $100,000 to 1 million, and companies that are small, less than $100,000.
Maaz, when you say 5%, is that just one person?
5% of 40. So that would be two, I think.
4 people.
Two people?
Two people.
Okay.
Yes.
All right. I like to think of people, not percents. Sorry.
Right. Yeah. So as I mentioned previously, we did an analysis about the relationship between having BIM VDC departments with annual sales of work. So this is kind of the annual sales of work that the companies had, and this is the total count of people, kind of what Professor Kim just asked for, of the number of people that were in that category. And then, so as you can see, the companies that were greater than $1 billion, 7 out of the 7 companies said that they had BIM and VDC departments. The companies that were from $100 million to $1 billion, there were 8 companies that responded, and 5 of those said that they have VDC departments, 2 said they don't. And this is where the trend shifts a bit. $100 million to the 1 million to 100 million range. You have 21 total companies that have responded. Only 2 of them have said that they have VDC departments. 19 said that they don't. And then all of the 4 companies that were below the $1 million range said that they don't have VDC departments. And that's kind of what the general totals were at the end of the day for the respondents. When asked to what extent their company utilizes technology to solve problems, 14 out of the 15 candidates that had VDC departments at their companies said often, while 1 said always. And the figure below shows the analysis of the other people who did not have VDC departments at their companies. So, and this is where it's interesting, because these respondents don't have VDC or BIM departments at their companies, but 1 of them has said always, 10 of them have said they often use technology to solve problems in their companies. 12 of them have said sometimes, and 2 have said rarely. No one said they never use technology, which is understandable that we live in a technology-prone world. And basically to understand where the respondents' current knowledge stands at this point, we asked them general concept about what they know, questions about what they know about automation and progress monitoring. Most said that automation is not being carried out in the progress monitoring realm in the current construction industry, which is not really correct, because currently companies like Doxel and Boston Dynamics are automating progress monitoring, and they've already started using it for progress monitoring purposes. It's not widespread, but it is something that is being done. Some did say that drones and 360 cameras were being used for automation and progress monitoring, and that was the highest level that people knew about automation. No one really talked about robots. No one really talked about using robotics for automation. So this is kind of from these answers, we kind of understood that this concept of using robotics for automation, automating progress monitoring is kind of new to the industry. Let's move on to the perception analysis. What were their perceptions before they watched the video that I just showed you guys? So when asked to what extent would you choose to have progress monitoring process automated or handled by a robot? So before the video, we have this normal distribution. 16 people were neutral as to whether or not they would want to have it. And this is kind of the distribution that we had. When asked the neutral people, when asked everyone like why they said what they said, this is kind of where we get into the qualitative analysis. The neutral people, most of them said 60% of them said that they need to learn more or they're unsure about the process, which is understandable, as they were the biggest chunk. And these people were that we need more information about this process. We don't really know. The people that said likely or very likely, this is kind of what their perceptions were before even like having them watch the video or like introducing the concept to them. And some of the most important ones, these are some of the most important ones. A robot can effectively, accurately, and routinely monitor progress on the job site. It would aid in daily operations, reduce manpower needed to perform the same task that could be reallocated to another area of progress. So basically what he's saying is, this is a menial task. This is a task that a robot, I think, can do better on a daily basis. I should be more focused on better tasks that have more creativity involved that I can, spend my time at. And this process, this response was really something that was interesting, because this person just said, I just don't want to do it anymore. That's why I'd rather have it done by a robot. And this person said, I would love to have this automated. Progress monitoring is something that we talk about doing, but we rarely do well. It usually gets pushed to the back barrier. An important point that we did get from all this is that this person in the second point said that this would save a lot of time, but there is a certain drawback to having this automated. And this drawback was that certain people might use the system as a crutch and not go look at areas of the job. Considering people tend to naturally drift to lazy behaviors, this could hurt field personnel understanding of the job if they do not physically go off the job. Now, reading this, I did understand what this person was saying, and this is pertinent to mention, and this is kind of what we talked about in the initial part of this presentation as well, that this concept is not a replacement from visual inspections. This concept of automating is an add-on to visual inspections. Now you won't have to always go on the site and conduct visual inspections. You'd go on site and conduct visual inspections when you're needed to. When you see there's a problem in the 360 pictures that you've captured, and you're going on the site to like have a better look at it. So this was an important point. After analyzing the reasoning of the respondents that said they were unlikely or very unlikely in those categories, three aspects that came about from their opinions. But they talked about cost and effectiveness. They talked about actual effectiveness of the technology, plus the additional hassle of maintenance. Like they were not sure whether or not this technology would actually be effective rather than just a waste of their money. And lastly, not applicable to their specific niches in construction, somewhere from residential to the communication wastewater related. This is kind of what they said. Basically, these last 8 and 5 people that were unlikely and very, very unlikely. So this is before watching the video. This is kind of what happened after watching the video. From the normal distribution, we moved to more of a double peak distribution. And as you can see, before we had this neutral part, these neutral people that were the most, now we can see that these neutral people have shifted towards, they've made an opinion, they've made up their mind, either whether or not they like this concept. To understand what this meant, only 7 neutral now, as compared to, like, after watching the video, as compared to the 16 earlier, people made up their minds. 17 likely as compared to the 11 earlier, 16 unlikely to use this concept for automation as compared to the 13 earlier. In total, there were 7 respondents that moved from the neutral, that were neutral and below the line, like they were unlikely before watching the video, to above the line, that their perception changed. They either were not sure or they were like, we don't want to do this. There were 7 people that said, yes, we do want to do this. We're likely to do this or very likely to do this. And here's some of what they had to say. I better understand the concept after watching the video. Could be a useful tool. We need to monitor, and this could be a more cost-effective and consistent way to do it. It is interesting, efficient, and safe way of capturing progress. For the people on the other side who had a shift in the other direction, there are 8 respondents that moved from a neutral perspective to below the line unlikely perspective. There was no one that moved from the likely to the unlikely perspective. So these people that moved from neutral and they were like, no, we don't want to do this after watching the video, these are some of the reasons that they mentioned. I don't see where the robot could get close enough to the project or intuitively know what to take pictures to make this a viable option. multi-floor buildings, terrain, and detail of photos. Now, this is important. He said a couple of things here. One, this robot would not automatically know what are the places that it needs to take pictures of. So this is something that can be automated. You can set a timer on the camera and ask the robot to capture photos at, say, 1 minute, at, say, 2 minutes, at certain points every single day, so that you capture data at that specific point. But this is something that multi-floor buildings, terrain, and detail of photos, this is something that was a drawback of the robotic technology rather than the process. And if you remember in the video that I showed you guys, I did mention that we should try to focus more on the process. This research is more focused on whether or not this automating the progress monitoring process would provide value for construction personnel, and rather than focusing on the technology that we're using for this research. Again, this video showed normal terrain and conditions that are not standard to construction sites. That is a good point, a valid point, that is correct. But again, it was the problem of the robotic technology. This robot was not able to traverse several floors or go on, say, really gravelly surfaces. Now, the respondents' perception analysis, that shifted and changed. The respondents who reported a perception change before and after watching the videos. When analyzing them collectively, when asked them whether or not they had a perception change and if they'd like to talk about it, this is what they had to say. Proof of concept in the video was very helpful. I can see more practical uses for it after I saw the video. And this is interesting. Robot to me, a large, clunky, heavy, expensive machinery. That's what he knew before. After seeing how compact it is, my fear is that I'll step on it or run over it without ever knowing it, which is understandable. This is definitely coming. Boston Dynamics' dog with a laser scanner has been shown off for the last year. To find the balance between price, maneuverability, and safety will be the key. The idea of automation is normally positive in our daily lives, but I don't know if it would ever be safe enough for a robot of any kind to be running around in and out of buildings under construction with workers on ladders, etc. And it would probably get run over pretty quickly. So some of the people are like really happy. They're like, yes, this is something that was really helpful. We like this process. Where other people were a bit more skeptical. They were like, yeah, we do like the whole idea, but we think that there's some safety issues. It might intrude laborers from doing their work, hit into them, get stepped on. So these are some of the drawbacks that they did mention. And the respondents who did not report a perception change before and after watching the video simply said no change in perception before and after watching the video. And most of them were those people who were from different construction niches that they just said it's not applicable to our construction niche. Talking about the safety analysis, this is the before chart of how safe would you feel working on a job site while an automated robot is taking its daily route traversing the site. So before watching the video, this is what people said. 15% said we'll be very, very safe. That is 6 people. 33% said that they'd just be safe, 13 people. Most of the people, they said that they'd be neither safe or unsafe. They didn't really have an opinion about it. So 20 people. And this is what happened, and one was very unsafe. This is what happened after watching the video. As compared to the 13 before, we have 19 people who feel safe. As compared to the 20 neutral, we have 14 people who are neutral. Most of them moved to the safe, very safe side. One guy did move to the unsafe side. One was still very unsafe. When we talked about the SWOT analysis, this is kind of what the SWOT analysis process looked like in the actual survey. So the respondents were asked to do an interactive strength weakness analysis, weakness opportunities and threat analysis in the survey. And basically what I said was, these are some of the attributes, and please drag them on the left side of the box you think they best fit into. Are they a strength, a weakness, an opportunity, or a threat? And this was basically left onto the respondents to navigate and just plug in different boxes. And this is the result that we got from the analysis. The biggest strengths that people saw in the entire thing that were reported was the utility or the ease of use and the automation. followed closely by the comfort and the speed of process. That this process would help increase the speed. It would be comfortable. The automation is good. They think that's a strength, and it's easy to use. We think it has value. It has utility. That's good. It was followed closely by efficiency, reliability of the process. The biggest weakness that we saw, and this is as expected, traversing floors on multi-story buildings. And as I said previously, it is definitely a weakness that we should work on, but it's something that's a technological weakness that other robots, say the Doxel robot, that is almost the same size as this robot, but because it has chained tires, kind of like what tanks have, that's why it can actually traverse steps and like go upstairs as compared to the wheels that our robot had. And after that weakness, the biggest weakness that we saw was this last aspect right here. And then the biggest opportunity that we saw was feasibility. They thought that this is something that could be feasible. Again, automation, speed of process was seen as an opportunity for improvement. Efficiency could be improved, reliability could be improved, and economy could be improved. That is something that we did not mention, that we failed to mention, I think, in the entire survey in the video, how much this entire thing ended up costing us. And that is kind of, I think, why they said that there's always an opportunity for improvement of the economy. The biggest threats were safety of the process. Again, as we said, whenever you're introducing a technology in the industry that can intrude with people, hit people, the construction industry is known for a litigious society. People like to sue each other all along. So, for example, if this robot ends up hitting someone, they might sue the company, even though nothing happens at all to them. And the biggest threat, again, was the economic aspect from this SWOT analysis. So from that analysis, what are the recommendations for future research that I had from all of this entire research? I thought that we should definitely consider variations across different regions in the US. The West would have a different perspective about automation and technology as compared to the Southeast. We should have a targeted research as well, a research that focuses just on commercial contractor, just on residential, just on heavy civil. That's something that could be worked on future research. Better technology, just like I talked about the Doxel robot, that could be used. It can traverse multiple floors. Automation of UAVs. If UAVs, drones can be automated, easily automated is the exact term that we should be using. That is something that would be great because it can actually traverse several floors, go on different heights. And as technology progresses, I see that there's a lot of areas of improvement for better technology in this research domain. Better programming, as I told Steve in my answer, you can do line following with it. Human tracking, collision detection, and avoidance capabilities is something you can program and add on to it. And lastly, linking it with third-party software like OpenSpace. What that would do is, as soon as you take pictures, those photos would seamlessly link with the drawing sheets on the cloud. And as soon as the daily tracking is done and all those pictures are linked to the drawing sheet on the cloud, all the stakeholders that have access to that website, to that cloud, the superintendent, project manager, the client, the owner, the architect, everyone who has access can on a daily, weekly basis see progress happening live. And that is something that can definitely be worked on. What are the conclusions that we got from this research? We saw that there was a positive response, a generally positive response regarding automation for structured progress monitoring from the industry personnel. Thus, we see that a penchant does exist for automating the progress monitoring process in the US construction industry. Industry validation or proof of concept for automation progress monitoring. Therefore, we do get industry validation that this is something that should be done in the industry. Many respondents found the process being safe and more reliable after the visual demonstration as compared to before it, once the video demonstration helped explain the automation concept clearly. Several respondents expressed not wanting to manually do the daily monitoring task anymore, and that's a big find for this research. And then lastly, several iterations are needed to improve the current technology that we have using RoboMaster S1, using Insta1360X. There are several iterations that can be done, better technology, to reach a level of utility for mass industry-wide adoption and utility of this technology. And then after that, these are some of the references that I use for my report and this presentation. And that is it from my side. On to you guys.
So Maaz, I think one of the things I found interesting is I think, instead of, I wonder how many people assumed that you were trying to replace the superintendent, because if it comes across to them like you're trying to replace the superintendent, there's lots of reasons why they would say, well, that's not really the approach you should take. And I think one of the things that you have not touched on and is this issue of quality, right? Sort of how quality is supervised. And if a superintendent goes out to monitor the job site, they're not just looking at progress, but they're also looking at quality. And, the robot, the picture is an indicator, but it's not as good as a person walking around looking at it. So one question I have for you is, what if you defined your lane much narrower and to just say, hey, this is not progress monitoring, it is progress monitoring photos.
Right.
We're only taking photos because that's also required on the job site. And then these photos can be documented for just the purpose of documentation.
Right.
And instead of saying progress monitoring, because progress monitoring is to a superintendent, it also includes this notion of monitoring, lots of other things apart from just progress, right? So they are interested in looking at safety, they're interested in looking at quality, they're interested in looking at how many people are where's the material laid down, how clean is the job. So all of those things they're observing along with progress monitoring. Instead, if you suggested, hey, this robot is really there to take, and perhaps it may be more palatable to people if you say, hey, we're going to take job site photos because we need to do that anyway. And then later on, as cameras get more advanced, as things like that, maybe AI technology sort of integrated into these cameras to where they can spot some quality defects or maybe compare to where it's supposed to be versus where it is, those kinds of things. I wonder if you'd have a better, or more people would be accepting of that. I'm interested in your thoughts on that.
Yeah, definitely. So you talked about basically 3 points: superintendent replacement, quality, and AI integration at the end of the day. So let me start off with superintendent replacement. I think this would be more of a concern for a laborer rather than a superintendent, or say a project engineer rather than a superintendent. Because usually the person going on the site taking the 360 camera or taking the camera is not really the superintendent in most cases, at least in big projects where you need progress monitoring done for, say, several years, almost every single day or every week. Usually it's the project engineer, usually it's the lower end person as compared to the superintendent. Now that you've mentioned that, I did talk to one of the laborers that I personally know, and I told this concept that I was working on, and this was something that he was really focused at, was that, hey, you're just like bringing in technology that would replace us. You're just bringing in robotic technology that would get our jobs away. And yeah, definitely, I think this is something that should be kept in mind And I think this was also a focus for us that, for say the project engineer, rather than doing this 100 times every year, why not? Why doesn't he just do this a couple of times every year? Let the robot do this for the rest of the times, and the time that he has saved now, he can spend on better, more creative tasks, problem solving, going on the site and actually monitoring quality. Again, taking this into quality now, that is something that, yes, you can see from 360 pictures and pictures as cameras get better, but again, we are not replacing human touch here. We're not saying that with this, a superintendent would just sit in his office all day, do nothing, never go look at the site, and he can see everything, monitor everything through his office, through these pictures. These are just to add on, these are just to help, rather than 3 visits a day. He can change that to 1 visit a day. In that 1 visit, he'd be more focused on quality rather than whether or not the work was done. And lastly, about the AI integration, there are actually softwares. I mentioned OpenSpace AI. There are softwares that actually link schedules with 360 pictures, and they overlay them together. And what happens at the end of the day is they use AI to see, say a beam is missing or a beam's length is not complete. They overlay the schedule, the Revit model, on top of the actual pictures, and actually see a difference in quality and issues with quality and issues with the project that way. So yeah, I think that's definitely something to consider. Did that answer your question, Professor Newt?
Yes.
Okay, cool.
So Maz, I had a real quick question about the robot itself in terms of, I mean, there's some things that it's limited on, and they're obvious. So in your testing, you took it to the construction field lab, and maybe could you explain the process, because the video shows you basically ran it on asphalt paving. What other terrains did you try it on, or did you? And thinking of a construction site, they've got mud and they've got water and other things that are not really good for machinery. So
Yeah.
what are some things you could speak to about that?
So we tried it on 3 different terrains. We weren't able to show that in video just to keep the video short. But one, it was the asphalt pavement. The other one was a gravel road. So a road that had gravels all over it. We ran it on that. And then the third terrain was grass, basically, wet grass actually, for that. And its performance in the gravel road or the gravel pathway was pretty interesting. It was able to traverse it. It was able to go about it. You could change speeds, go slow, go fast. When it was going slower, it would actually be less bumpy, but it could go straight and back and travel. It wasn't able to go sideways though. That was one of the things that whenever like you want to move it sideways in a dirt or a gravel pathway, it would just start digging its tires into it and creating skid marks basically. When we tried it in the wet grass, the grass was it was like halfway till halfway the height of the tire. So it was like not really well trimmed grass. And because it was wet, it wasn't really able to travel or traverse in that. It kept skidding, the tires kept skidding in that wet grass. So these are the 3 terrains that we tested the robot out on.
So based on that, what would you say, when would you say a robot like this would be usable on a project?
I'd say when it would not be useful is probably the excavation and when you're laying the substructure. That is some of the, that is a place that it might not be super useful because there's a risk of having it fall in the ditch or the excavation. As soon as the substructure is up, it's dirt all over. This robot can traverse that. And especially again because you saw it traveling the asphalt roadway. As soon as the substructure is up, the concrete slabs laid, after that it'll just be normal. It'll be able to go pretty easily. So everything after the substructure, everything after when the foundations are laid and everything after that.
Okay, well, as you had mentioned, sort of linking the pictures that it took back to a drawing so that you could kind of keep track of where it was. I was kind of thinking, turning around the other way, I know you programmed the direction and the turns and the distances that it ran. Did you look into using a drawing to map out the path the robot would take through a building? And you mentioned drawing a line or something like that, but using the drawing to actually get those dimensions, how repeatable or how accurate are those movements, did you find, based on the program? What did it actually do, or did you look at that?
Right. So where the
accuracy.
So where the current level of technology stands at this point, we can actually go into a drawing sheet and link a path in the drawing sheet and then press go and the robot goes. That involves, like, this is something that I can see happening in the next 1 to 2 years, but right now that link is absent. And hopefully more research work, as if Professor Kim has some other student do this, that they can definitely work on this. Currently, what actual contractors can do is take a drawing sheet, decide where they would want the robot to traverse in that building, put spots down in that drawing sheet on their tab or their sheets as to where they would want pictures taken, and then use a tape of whatever color and mark out that path so that every day that robot can go through that path. But right now, automatic integration of drawing sheets online to the robot is not currently capable. The robot's not capable.
I was thinking more or less along the lines of you draw a line on a drawing and then you determine what the lengths and the angles and the distances are for that line and do the programming just like you did. How accurate are all those movements and distances that it actually traverses when you put it in the program? If you say go 5 meters, does it go a little less or a little more, or is it pretty accurate?
Right. That's actually a really good point. Because the lengths are pretty accurate, when it says 5 meters, it is 5 meters. If you're just sitting on your computer looking at a drawing sheet and detailing out distances and angles from that, it should be able to 95% at least. You can put the robot where you decided it's going to start from. You had programmed it at home, not even on the site. Press go. 95% of the times, it would be perfect. The 5% would be human error, and I think you can fix that pretty quickly. But the more you practice on it, I think you can get pretty close to 100% accuracy as well after a couple of tries. So that's actually a pretty good idea people can use.
And I was thinking coupling that with maybe some of those points that you were talking about where you wanted to make pictures. Obviously, its movements now are predicated on the accuracy of previous movements if you're going through a complicated path through the building, but at some particular points be able to assess and correct its current position to then pick up the next few moves or whatever that it needs to do.
That's actually a really good point as well. Say, for example, it bumps into something. It bumps into an instrument. It hits a person and it goes off track. You can put trackers, certain symbols that you can program the robot and tell it, and it's simple programming as well. You can tell it, hey, whenever you see this symbol, this is what you got to do. This is where you need to start from. Or if you hit someone, look for the symbol around you. Or hit someone, step 5 feet back. Like, there are correction measures that you can take. And I think those trackers can really help. You can place them on walls, on certain intersections. And as soon as the robot sees them, he can, correct its path and come back at the proper path that it's supposed to go on.
I know a couple of people reference safety or stepping on it or it running into somebody and causing a ladder or something like that could be a problem if someone was on it. Did you look at, or did you talk with any of them about doing these things when the project was not occupied, like during off hours, where that wouldn't be a problem if that would affect their views like that?
Yeah. I didn't specifically talk to someone about this and tell them that. And I think this is something that as soon as, say, COVID restrictions lift, if you can go out an actual construction site, show them how this works, program it for that construction site, spend 20 minutes programming it for a construction site, show a superintendent how it's done. Once he sees the process by himself and looks at the results, then you can actually go back and forth and answer questions that he has. For example, what would be the ideal time to actually have this robot go? And it could be twice a day. It could be before construction starts every day at 6 a.m. or 5 a.m. And then after construction ends and everyone goes home. So that's actually, again, yeah, this is something that people should consider. And that would be the best time, obviously, when people are not around.
I could see Auburn teaming up with a robot vacuum company or something like that for some research. It's like the robot in my house vacuum, like it actually puts out a map. It actually has laser scanning and all that built into it for a really affordable product. And it's able to, build a whole map of the floor. You just hit go and it goes. So I wonder if maybe that's a potential future for it, just teaming up in that regard. And then like I could honestly see it's funny, before this, my perception changed. I thought, yeah, it's still going to be a ways before robots are, useful enough to do that. But if we were to get it to the point where it could at least follow a tape around, like a green tape or something, and if it could charge itself and upload the photos to the cloud, I'd buy one for every floor of a couple projects just to try them out. I mean, $1,000 is very cheap to have that sort of functionality.
Right. I've got this same response from a lot of different, when like at the end of the day, I asked them, hey, any last words? A lot of the people from the industry had a similar response to yours. And a couple of them also said, hey, if you want to try this on our construction sites, we're more than happy to like link you to some people that are actually on live construction sites and you can try it on there. We'd love to see how this can be beneficial. So yeah, like this definitely has potential. About what you said, currently it can do the first two things. It can follow a line. It also can it also will be able to throw things on the cloud. I did talk to the people at OpenSpace AI. One of the things that it cannot do at this point is charge itself until we get, say, solar-powered RoboMaster or a robot. Probably can't till then. Right now, it does have an insertable battery, so it's kind of like your camera battery, not really a phone battery. Like you take it out, you charge it, and then you put it back in. So that's something that someone would have to do manually right now at this point in time. But in the future, well, there are literally no limits to what can be done.
So Maaz, finally, based on the results of your survey, what is your conclusion that you think, according to your aim, your aim was to ask a question whether or not this is palatable to the industry? What is your thought on that?
My eventual thoughts are that there definitely is a need. It's not just academic people saying, hey, we have done these analyses based on the literature that's present, and we think it's something that's needed. The industry people are saying that, majority of them are saying that this is something that has a lot of potential. It is a need, there is a need for this, and that it's, as soon as the technology catches up to it, some of the important things that were mentioned, traversing different floors. So if you have a multi-story buildings, you want it to be able to do that. At this point, you can take this robot, put it at different floors, but again, we want to reduce human intervention as much as possible. But as soon as the technology catches up to that, you have, say, a drone doing the same thing, or a robot that can travel different steps, and say, just like how Steve said, a robot that can charge itself. These are some of the things that as soon as the technology catches up to it, this is definitely going to be booming. And this is something that would definitely be on almost every construction site in the future. That's kind of what my conclusion is from the entire research response.
Well, great job, Maaz. Does anybody else have any other questions? And maybe we could break out in a quick room here and talk about Maaz's presentation and thesis. All right, well, let's do that real quick. I'm not sure how we do that since Maaz has the floor here.
Stop the recording, pause it.
You can go ahead and you can end the recording.